Uh, Good afternoon. First of all, let me start by thanking the organizers for giving me an opportunity to present this work. So today I'm going to speak about extreme dynamics and relaxation in quantum gases, but I'll also discuss a case of classical gas and so on. So, the first part is going to be on extreme dynamics in quantum gases that obey a hydrodynamic approach. This is work done with Ritvik, who's a student at ICTS, and my colleagues Abhishek and Samriddhi at ICTS. And in the second part, I'll speak about dynamics of some gas called the Rees gas, and which also has some interesting connection with cold atomic gases. And also I'll try to discuss some earlier work in this direction. So let me go to part A, which is extreme dynamics. So we are interested in a class of quantum gases which obey extreme dynamics, that they're highly out of equilibrium. So let me give a quick take-home message. So what we show is that evolution of gases released from very strong confinement. So we have a gas and we confine it very strongly and we basically let them blast. And this has been, we studied this analytically and numerically in 1 and 2 dimensions. And you can show that such extreme initial conditions often lead to long-time self-similar solutions, both for density and velocity fields. And we derive some exponents as well as functions. So basically, how does density field look at fairly large times? And these expanding gases develop a shock front, and one can study the size of this cloud of gas, and that shows a power law in time. And you can show that the associated exponent is related to some exponent that appears in equations of state of the gas, and we'll end with some relaxation dynamics of trapped gases. So before this, let me just give a quick motivation. So, I mean, here in this audience, I don't need to spend much time on motivating cold atom dynamics, but non-equilibrium dynamics of cold atoms has been subject of great interest theoretically and experimentally, and people have been performing experiments for free expansion of trapped gases. And there is theoretically an understanding of via hydrodynamics and sometimes generalized hydrodynamics. And there has been immense activity in bosons, fermions, mixtures, and so on. And studying such extreme dynamics gives you some idea of intrinsic interactions that lead to this kind of exotic collective behavior. So I hope the setup is sort of clear. So irrespective of your system, we just jam the cold atomic gas, which is assumed to have some sort of hydrodynamic description, and then we release it. And then we ask, how does the system expand? Okay, so that is the basic setup. So what is generally far less understood is this kind of extreme dynamics. People have studied dynamics away from equilibrium, but what happens if it is far, far away? And there are some earlier works where this is an experiment theory collaboration with a group of John Thomas many years ago, where we showed that there are shock waves in strongly interacting Fermi gases. So here you basically separate two fermionic clouds, you let them jam, and then eventually they will develop shock waves. And one can understand these things by a fairly simple hydrodynamic description. And one can also study relaxation dynamics towards the steady state. But these things are still less explored, and evolution that mimics a blast can arise from sudden release of substantial amount of particles or energy. So basically you can either put lot of particles or you can put lot of energy at at the central region. And so obviously there are a couple of natural challenges. So one challenge is establishing rigorously the collective hydrodynamic description. So it is often not clear what is the hydrodynamic description of such a system, especially when it is far from equilibrium. And even if you have the hydrodynamic description, you generally don't, there is lack of analytical solutions very far from equilibrium. So what I mean is when you are close to equilibrium, But still away from equilibrium, you can do linearized hydrodynamics, you can get something about sound waves, and so on and so forth. But if you start from something very far from equilibrium, getting analytical solutions is also hard, even though you may have some idea of the hydrodynamic description. Okay, so let me just quickly motivate the blast problem. So one of the most interesting results in this problem are so-called self-similar scaling solutions. So basically, what happens is that when you have a blast, you can write self-similar solutions, and I'll explain what I mean by self-similar solutions in the next slide. And then this was discussed long ago by Taylor, von Neumann, Sedo, in the context of atomic explosions. And to understand the evolution of hydrodynamic fields, namely density, momentum, energy, is sort of is an interesting question. And there has been recent interest in the blast problem in some versions of hard rods and so on and so forth. So and trying to understand the blast not only from hydrodynamic point of view, but also by microscopic simulations of particles that are initially in some sort of blast initial conditions. Okay, so these are some very interesting recent works, and we want to ask these kind of questions in the category of quantum gases, and especially there are class of quantum gases that are known to be well described by hydrodynamics, as I showed in the experiment in Duke in the group of John Thomas, that we studied shock waves in unitary Fermi gas, very strongly interacting Fermi gas, and fairly simple hydrodynamic description actually reproduced the experiment of shock waves, which is highly far from equilibrium phenomena. Okay, so please stop me if you have questions. So now let me these blasts are basically the physics associated with this are basically originating from fascinating collective dynamics of constituent particles, bosons, fermions, and so on. And it's in principle possible to capture these things through a coarse-grained hydrodynamics, and one can consider near zero temperature case, which is reasonable in cold atomic experiments. So we have a very simple hydrodynamics equation, which is a continuity equation and an Euler equation. So, and this is what we call specific enthalpy. This is related to pressure and basically related to the equation of state. So all the details of the cold atomic gas enters here in this W. Okay, and this is your inevitable harmonic trap or whatever trap you need in the setup. And one can ask what happens if we study evolution of such equations with extreme initial conditions. Like my density is basically almost like a delta function at the center, and my system is very big. So what will happen to that density evolution? That is one of the questions you can ask. So now let me motivate this further in terms of our current understanding of interacting gases. So recall this quantity. This is W of rho. So this is the thing that enters into these hydrodynamic equations. Now let us remember that W of rho I have written as d rho to the power delta. So we are going to study a class of models where W of rho is basically rho to the power delta. Okay, so and it is interesting that a large class of models actually fall into this category. So Thomas in the previous talk talked about Liblinger gas. One can show in certain regimes that you can have situations where the Liblinger gas basically has delta equal to 1 if it is weak coupling, and in the Tonks limit it can be delta equal to 2. Most well-known and these things are the unitary Fermi gas, where delta is 2/5, and then you have some plane wave limit, and you have in higher dimensions you can have weakly and strongly interacting Fermi gases. So these are various deltas that actually appear. So it is a fairly realistic scenario, and this kind of equation of state, if you want to call it, is very deeply connected to other systems such as quark gluon plasma, where they have systems which are known to be very similar to strongly interacting Fermi gases. So these are some nice references I've kept here. And also, if you are interested in electronic hydrodynamics of graphene, some astrophysical gas dynamics, these kind of relations do appear. So it is useful to study at least one class of hydrodynamic equations with this W of rho. So yeah. Yeah, so it is included in D and in some sense in delta. Yeah, that's where it is. So for rest of the purposes, you can is basically the same. Yeah, this is again slightly complicated. You are assuming that there is a hydrodynamic description and so on, but once there is, so this is where it enters. Yeah. Okay, and so this is part B of my talk, where I'm going to talk about family of Rees gases. This is potentially interesting for ions, where you have particles with all-to-all coupling, and then you can actually show that in this family you can realize many of these deltas, but this I will speak in the next part. Okay, so now let me go back to a very simplified version of our equation. So please look at these equations. So these are very simple looking equation where details of your system go here. Okay, so it goes here. So basically, and this is, so we will first consider a case where we have zero background. So there is nothing. So we call it vacuum. And the initial condition is a spatially localized mass. Okay, so we have a spatially localized mass, and then we let this system evolve. And we find that at long times, you have these self-similar solutions. So you have these solutions for density and velocity, where you have this kind of self-similar solutions. And these exponents associated with the densities and velocities are basically related to delta that appears here. Okay, so recall that delta is basically coming from here. And basically pressure is related to density by rho power, I think, some function of delta. So basically, delta is basically telling you what the equation of state of the gas is. Okay, so we found that you can have this kind of scaling solutions. So let me just quickly go through how we get it. So, okay, I'll not go through the algebra, but important point is that you have this thing, you will see the plots in the next slide, that this thing will just blast, and then there is this blast front which will go, okay, which will expand. And you can derive many things using these Rankine-Hugenow boundary conditions and so on. But important thing is the size of the blast. The size of the blast actually goes as T power B, where recall that B is nothing but 2 by delta plus 2. So if you are able to measure the size of the blast, which is a fairly easy thing to measure in principle because you are just measuring the size of the cloud after the blast, you can actually infer what would be the equation of state of the underlying gas. So this is how the blast radius expands. Okay, and then and these are the precise scaling functions and so on. So I'll just show you some plots. So that is finding analytical solutions, and then one can actually do direct numerical simulations. So without bothering about these analytical solutions, these are slightly complicated simulations because these are extreme dynamics because of extreme initial conditions. But nonetheless, you can do it, and you can pack all the atoms in a small Gaussian here and let it evolve, and then you can compare numerics and analytical predictions and so on. But let me actually show you the plots. So let us forget the right-hand side column. It's all velocity, but let's just focus on the density. So this is my initial condition, very, very localized, and this is how it will blast. Okay, and this is how the blast expands in space. And at late time, this is fairly early times, and late time, this is how the blast will look. You see the blast front is expanding, and then you can completely scale it, and they will all follow this universal scaling forms. Okay, so this is the result, and this is done in vacuum. So basically, except that lump in the middle, there is no density. Okay, so this is, so please let me know if you have any questions. Yeah, yeah. Yeah. These are still solutions of the hydrometry. So that is a very hard problem to actually do the microscopics of the gas itself. Yeah. We'll try to do something about it in part B. So yeah. Okay. So all right. So one very interesting thing about this is it is independent of details of a large class of initial conditions. So basically, notice that here we did a slightly asymmetric profile for the density, but it is still localized. But it turns out that finally it actually reaches the same scaled profile. So these are extreme solutions, and they are basically, as long as your initial condition is fairly localized, it doesn't really care whether it's a Gaussian or it's a double Gaussian and so on. Finally, it will go to the scaling solutions. This is what we find, and there are some subtle points about this, but let me just go to the next case. So, so I just want to say one thing is that in typical time of flight experiments, you actually just release your gas. So in principle, one should be able to do a systematic analysis of radius of your blast and actually test these predictions in cold atomic gases, especially in unitary Fermi gas or some hydrodynamic system. And we have been trying to contact people, but it's not so clear at the moment. And now I'll go to finite background. So here, basically, the story is similar, but in addition to your localized initial condition, there's a background, and this is so what we notice is that okay. So let me just say the important things here. So the localized mass density will propagate and simultaneously spread, and at sufficient large times, the excess density becomes small, and one can do linearized theory to predict speed of sound. Okay, so I'll skip the calculations, but if it is linear perturbation theory, you can immediately get the speed of sound. And in fact, earlier experiments in many gases, bosonic or fermionic, usually you're after the speed sound first, and then you are interested in away from equilibrium, highly away from equilibrium dynamics. So here also you can sort of do these calculations and get the scaling forms and so on. This is also useful because in many cold atom setups, you might have a finite background. So you can imagine you have a situation where you have a very shallow trap. So there is a gas, but then you have an additional red dew-tuned laser to create a Gaussian bump in the center, and then you switch off your red dew-tuned laser. So you can imagine that in principle you can relatively easily do this experiment. Okay, so here is again focus on the left column for the density, and we notice that the shock in this case actually goes linear in t. It doesn't go as t power that function of beta, function of delta, and then one can show excellent agreement between numerics and between full-scale numerics of the hydrodynamic equations versus the scaling solutions. So 16 minutes. Okay. So now I'll switch gears a little bit. So till now it has been about blast. So we really didn't care about finally reaching some equilibrium, right? Because we were just interested in the blast solution. But now let me change the problem a little bit. So imagine you have a set of equations like this, but you actually keep a harmonic trap. You don't switch off your harmonic trap, but you have a small dissipative term. And then it is easy to show that the steady state solution is this kind of dome, 1 minus x square power 1 over delta, where again delta is related to the equation of the state of the gas, or whatever gas it is. And if you do small perturbation and some calculations, you can actually calculate analytically the damping rates and so on and so forth. And you can study how the system in a harmonic trap with some dissipation relaxes back to this steady state. So what I'm saying is that if you have a harmonic trap, then your steady state would be something like this. So it will be 1 minus x square power 1 over delta. But if I create some perturbation and let it evolve, we can make analytical estimates of what the relaxation time of this back to the steady state is. Okay, so this is slightly different from the blast problem that I discussed in previous slides. So, so you can not only get the damping rates, but also the late time functional forms and so on and so forth for this, for relaxation of gases in a harmonic trap. So going back to the blast, so we can again do the two-dimension case. So you see that in two-dimension we have this a small delta function here, and here you see the shock front, and then you can find the scaling solutions and how the radius of the blast changes in time, which is a power law in time. So the radius of the blast goes power law in time, and this is actually an old story. Even the Trinity blast explosions, you can actually show how the radius of the Trinity blast grows with time just by some dimensional analysis. So here we are trying to calculate these kind of things for the cold atomic gases. Okay, so I'll just end my part A by saying that we studied evolution of gases released from strong confinement through hydrodynamics. We studied the long-term self-similar solutions, derived the scaling forms and scaling exponents. And the shock front goes as power law. And this is important. So if the equation of state is rho power delta plus 1, then the front goes as t to the power some function of delta. So you can use this to get this, or if you have a gas about which you have no idea, you do this blast experiment, and from here you can get back the equation of state. So this could be a good way to infer the equation of state. We studied relaxation, and this is really well suited for time of flight measurements. And if one can test it with absorption imaging, that would be very interesting. And there are many non-trivial generalizations. So higher dimensions is quite non-trivial, especially if you have anisotropy, or if there's because of the geometry and lack of symmetry, you can have very different blast problems. You can extend this to open quantum systems. So in principle, some exciton, polartron fluids, and so on. Reese gas I'm going to speak about a little bit in the next part. And you can really use these results for understanding hydrodynamics of quark-gluon plasmas and so on, because they really they really show very similar hydrodynamic behavior as strongly interacting Fermi gas. Okay, so I'll just go to second part. I will not spend too much time on the second part, but if there are any questions, please let me know. Yeah. Yeah, so we don't actually derive the Euler equation from microscopically. That is actually in the second part. I will show an example. But for example, let's say you know the equation of state for a ideal Fermi gas. Then we know that very strongly interacting Fermi gas in the unitary limit doesn't have any scale. So basically, it just renormalizes the equation of state of the ideal Fermi gas. So this is sort of established many years ago. So for certain class of models, we can actually we know the equation of state. So for those, you can just write the Euler equations. Yeah. Yes. Okay. So very important question. So notice that if you actually study the Bose gas, no matter how you do it, you might have higher derivatives of density. So, and higher derivatives of density will actually fight the shock. Actually, what will happen is that when the shocks are formed, those high derivatives will kick in and they will create oscillations. And sometimes people call it dispersive shocks and so on. So we didn't do that here. We are basically, we are not at all thinking in terms of using Gross-Pitevsky and writing it in hydrodynamic variables. We are just saying that let there be a gas where it is in a hydrodynamic regime. So yeah. So yeah. 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 No. So the particle is number is also conserved here. So this is just dissipation. So you just, it's like viscosity term. Okay. So there is no, the particle number is still conserved. Yeah. Okay. So some of these questions might slightly get answered in the second part. So I will. So second part is going to be on classical systems, but for many reasons, for large class of questions, maybe even the quantum versions of this is going to work. So let me start with the problem. So Rees gas. So this is an example which is highly relevant in physics and mathematics and so on. So this is basically a bunch of systems with 1 over xi minus xj power k interactions. Everything is coupled to everything with a power of k. Okay, and it could be all to all, or it could be in some finite range. And then there is a kinetic energy term, and then there's a trap. So this is called the Rees gas. And in particular, I'll talk about finite range Rees gas, but it's not very important for what I say. It could be all to all Rees gas. So every particle is coupled to d particles by this 1 over xi minus xj power k. So notice that this kind of power law interaction is actually relevant in cold ions, and one can actually get certain, at least some class of values of k if you have cold trapped ions in almost purely 1D. So if you have pure 1D chain of cold ions, you can actually recover this kind of Hamiltonian. So we'll assume n is relatively large and system is at some reasonable temperature T. Okay, by reasonable temperature I mean it is not very low that you can ignore it. Also, it is not extremely high. So it's So that's what I mean. So okay. So this is a model. So notice some interesting thing about this model, that particles cannot come too close to the center because they will diverge, right? At the same time, they cannot fly away because of this trap. So it's a gas of particles that are basically sort of stuck in some sort of a trap. They cannot all sit at the center. Okay, so there are variety of k values for which this model is very important.
Manas,
Yeah.
there's just one question. So you said so there's a sign of k, right? So if k is odd, then it becomes attractive.
No. So okay. So let me tell you. This is very important. So we assume that this relation is satisfied. Okay, k has to be greater than -2. Okay, so this sign of k is put such that the gas will always be repulsive. Even if k is negative, it will be repulsive. Okay, so
assuming j is
assuming j is positive. Yeah. Okay, so that is the thing. But I'm going to talk about a particular value of k for my numerics. So so there is this. Okay, so let me explain what is known. So the density of such a system for k greater than 0. So let me just be a little more specific here. For k greater than 0, the density of such a system can be extracted by minimizing some free energy. Okay, so where there is a temperature here. Okay, so basically, if you give me a temperature and ask me what is the density of the system, I can basically minimize this free energy, okay, and get the density. So you can imagine that the density will actually be, if the temperature is 0, the density will just be like this, okay. More or less, you can show that it is some generalizations of a semicircle. But if there is temperature, the density basically is slightly smoothened out, okay. But this is the exact expression in the large n limit, and this is the truncated Riemann zeta function, which is important, and this term is very crucial to. This is the term that contains the information of the k. Okay, so depending on k, the shape can change a bit. Okay, so then now the question is somewhat related to what Anna was asking. Now one can ask this question. So now I know the microscopic model. I can do Newton equations and do the microscopics. I sort of know the hydrodynamics for the model. It's a bit non-trivial, but we know it from some earlier works. And then the question is, can we compare hydrodynamic simulations with actual microscopic simulations? Okay, so that is the question. So Okay, so I'll not go into details, but you have to follow a very careful procedure so that you are comparing the correct parameter set. So basically, this is the microscopic equations. Very simple, right? These are just the microscopic equations we have to solve. But it's like a little complicated because there many particles are interacting here. But nonetheless, it can be done. And hydrodynamic equations can also be written. So let me just tell you how the hydrodynamics looks. So let me not go into details. So first equation is very easy to think. It's just a continuity equation. The second equation, this term here is basically the Euler term. So this term here basically can be derived exactly in large n limit. Okay, so this is very important because only by knowing this term you can make the comparison. If you try to randomly guess, you will never be able to compare microscopics and hydrodynamics. And this zeta d is precisely going to give you the right coefficient. This j times zeta times k here. And then we add some bulk viscosity and thermal conductivity terms, and we also have temperature here. So what are the crucial steps to obtain the above equation? So you use collective field theory techniques to get the free energy from which one can get the pressure. Okay, so there are some techniques. You start from microscopic setup, and then you write a collective field theory, and then from there you get the free energy, and from there you get the pressure. Then take that and put it in the Euler equation. So that part is sorted. Okay, so which is the most important part because it is supposed to tell you, be able to tell you whether it agrees with the microscopic theory. Then you can either write it in energy or temperature, the third equation. And you add some viscosity and thermal conductivity terms because deriving these things from microscopics is much more complicated. And then you compare. So let me show the comparison. So, so this is k equal to 1.5. Okay, so recall that k was this one, xi minus xj power k. Okay, so k is 1.5. And this is how I start, t equal to 0. And then this evolves, and this is the fitting parameter. So I'll tell you a little bit about this also. But this is in the thermal conductivity, this dissipation, not the Euler term. We don't do any fitting. Okay, so this is microscopics, this is hydrodynamics, and this is the steady state. So steady state, the microscopics and hydrodynamics and the expected steady state works very well. So steady state is that minimizing that free energy equation. Okay, so and this is the comparison in time. So you see that this is just a particular example of an initial condition. I could have studied some other initial condition like Gaussian initial condition and so on. So notice that this is not very extreme initial condition, right? Because I said more or less the density will look like this. So I might have just started with some density that looks like this. So it's not really extreme, okay? So there is good agreement between microscopics and hydrodynamics. These different colors here are microscopic and hydrodynamics. And we studied a slightly extreme condition, the Newton cradle. So Newton cradle is slightly extreme, right? So if your expected density is like this, if your expected density is like this, but I start with some initial condition like this. So this is extreme. I mean, but it doesn't lead to blast, but this is still extreme. So we do that, and we see actually that there is a very good. So this is the steady state. So the steady state really has to agree. Okay, that's also not fully obvious, but we are not very surprised that the steady state agrees. But here we notice that the time, you see the time also over a function of time, hydrodynamics and microscopics match. So maybe somewhat related to Anna's question, you see that if T is, so what we notice is that there's a fairly big window of this where things match. So it's not really that we precisely have to tune this kappa and zeta and xi, but at extremely early times there is a discrepancy. Okay, at extremely early times there's a discrepancy, but it already starts agreeing at times which are much below the equilibration time scale. So if the equilibration time scale is 2000, we start seeing reasonably good agreement from 100 onwards, after which there is still a lot of non-trivial dynamics to reach the steady state. Okay, so I will 2 minutes. Okay, so I'll just show this. So actually, I'm done. I'm done. So this is how it would look. So this is how the comparison would look. You see, this is hydrodynamics and microscopics versus each other. So this thing is going. This is the initial condition. This is 2 blob initial condition. And it keeps on going. There's a lot of dynamics happening, still far from steady state. But then eventually at around 2000 or something, they settle down to the steady state. And this is another representation. And we also make similar comparisons with the other fields. So I really didn't talk about velocity field or temperature field, but more or less, so one has to make a comparison with all the hydrodynamic fields that are that are involved. So, okay, so I'll so I just wanted to say that there is so more or less for any value of k, eventually the belief is that things will reach a steady state. Okay, especially when you have finite range interactions. But there is a particular case when k is infinity, where the system starts behaving like hard rods. And we showed earlier that this is a very strange system where it really doesn't seem to thermalize, although hard rods in a harmonic trap is non-integrable. So there's a particular limit of this Rees gas, which is k going to infinity, where things are a little subtle. Okay, so I will end by saying that we did microscopic and hydrodynamic comparison, and we studied fairly extreme initial conditions even in the second part. Here also it will be interesting to compute self-similar solutions, and there are certain parameters in K where there are some integrable points and so on and so forth, which we have to still explore. Thank you.
Okay, great. There were a lot of questions during the talk, but are there more questions now? Yeah, please.
In the first part of the talk, you had considered the zero background case. In real experiments, you have different kinds of collisions, like you have like one body collisions. You cannot really ignore the background. So you can have one body collisions or two body intra-cold atom collisions, or even at higher density two body collisions. So can you take those effects into account in your model?
Yeah, so okay, so not so sure about that. I mean, certainly, at least for the fermionic case, you can do some higher order corrections. You can incorporate it in the hydrodynamics, but it's not clear whether we can incorporate the kind of things that you are saying. But I just wanted to say that even by zero background, I mean, what I mean more is that for, just even in terms of time of flight, like let's say you just have cold gas and you just release it, and then you just measure the size of the cloud. Maybe not at very late times, because then maybe it stops becoming hydrodynamic. But at some intermediate times, if you measure, it should agree with these things. So if it stops becoming hydrodynamic is the real problem. But if it doesn't, if it remains hydrodynamic and we miss some collision terms or something, we might be wrong in our prediction of the exponent with which it grows, because maybe it has changed the equation of state or something. But if it is hydrodynamic, our belief is you should still get this power law behavior. Yeah. 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 For part B or part B, I guess, right? Yeah. Yeah. No, part B, we have looked at the velocity profiles, and it is agreeing. It is the same level of agreement as the density profile. The temperature profile is not yet fully compared, but no correlation.
Do you expect some endpoint correlations to stop corresponding for large n or something?
So microscopically, we should be able to calculate correlation functions. Now I have to think about in hydrodynamics, what does it mean to, I mean, maybe density coefficient from hydrodynamics, we might be able to calculate, but their question is what to calculate also. So we haven't done that, no.